Assalamualaikum and good day everyone. In the last lesson, we learned what a metric is. Rows, columns, and entries arranged neatly in a rectangular form. Now, we will discover something new. A special number that can be calculated from a square metric. We call this number determinant. The determinant tells us something about how the number in a square metric are arranged. You can think of it like the balance of the matrix. How the entries or the element across its diagonals compare to each other. Sometimes that balance gives a large number, sometimes a small number, and sometimes exactly zero. Let us start small. For 2 times 2 matrix, the determinant is found by multiplying 2 diagonal. First, this diagonal, and then subtracting with this diagonal. So, how it is calculated? We'll multiply across one diagonal and multiply the other diagonal, and then take the difference. Let us try one together. Look at example 2.12. For this metric, start with the main diagonal, which is 2 times 2. Subtract to the other diagonal, which is -4 and 1, which should give you +4. So for A, its determinant is 8, and B, do the same kind of calculation and you'll get determinant of -8. Next, what about a 3 times 3 matrix? The idea is similar, but now we have 3 diagonals going down and 3 diagonals going up. We can use a pattern called Serre's rule to help remember it. Using this rule, this is how you should do it. Right, we have C1, C2, and C3 as the original matrix. So we need to add the C1 and C2. We need to copy the C1 and C2 to this side. So now from 3 it becomes 5 columns. Now that we have these 5 columns, alright, we will multiply it left and right. So we'll start with this left side. So multiply it, multiply, and sum everything. And then we'll multiply this, multiply this, sum everything, and after that you are going to subtract those 2. So from the subtraction, you'll get one value that represents determinant. You can try to do example 2.13 by yourself and see if you get the answer. For bigger matrices like 4 times 4 or 5 times 5, drawing diagonals becomes messy. So instead, we use a method called cofactor expansion. It breaks a big matrix into smaller ones, step by step. We are going to have minors and cofactors. When we remove row and column from one matrix in order to look for a determinant, what left is called minor. Right? If we remove, let's say, this column and this row, the one that is left is called its minor. And when we give each minor a sign, whether a positive or negative based on its position, that is called cofactor. Together, these minors and cofactors help us to calculate the determinant more systematically. Now, let's try to demonstrate on how to use minor and cofactor in finding determinant. Let's find one example of a minor and its cofactor. Suppose that this is the matrix that we want to look at. So the question wants us to look for M12 or minor for 1, 2, element 1, 2. So let's first determine what is the element of 1, 2. So we have row 1. So we just consider it out like this. And we have column 2, which is this one. So what's left is actually the element that we'll need to calculate to find the determinant for that minor. So how to calculate for determinant again? Now we have 2 by 2. So 4 times 2 minus with 6 times 7. Okay. That will give us negative 34. Now that we have its minor, let's look for the cofactor. Now, in calculating for cofactor, in general, this is its formula. It will be negative 1 to the power of I plus j times with the value of the minor. So, what is actually the cofactor that we're going to look at is C12. So basically, if you try to input it in the formula, it is negative 1 to the power of 1 plus 2, right, from this, times with the value of M12. So when you do the calculation, we know already that the M is negative 34. So basically, we'll just need to times it with negative 1 to the power of 3. So negative 1 to the power of 3 will give us negative 1. So negative 1 times with negative 34 will give us 34. So that is the calculation for one minor with its cofactor. So basically, this is for M12 and C12 related to this element. So proceed with other element, do the same things. If it is actually M11, so you're going to eliminate 1 and 1. So the calculation will be using this element. If it is, let's say 13, so 13 is at this point. So basically, eliminate. So this will be used to calculate for M13 and C13. Okay, so we are still going to have certain things to discuss. For example, the reason we calculate for determinant. But at this stage, don't worry about what the determinant represents in the equations just yet. Just think of it as a special number, a special summary number for a square matrix. A number that changes when you swap rows, scale rows, or rearrange element. Later we'll use determinants for many things. So we'll use it to finding inverse matrices, solving sets of equations, and checking special properties of systems. For now, your goal is simple: learn how to calculate them and spot patterns confidently. So you have learned on how to calculate for determinant when the situation is less complicated, which is for 2 times 2 and 3 times 3, where you can use a diagonal way of calculation directly. And we also have more than 3 by 3, which is 4 by 4 onward. Actually, they are using the expansion, right, using cofactor and minus. Next, now that we have learned about how to calculate the minor and cofactor, the next definition talks about cofactor expansions. This is one way to calculate for determinant by just looking at the one column or one row. And of course, when we are talking about choosing any rows or columns in finding determinants, right, the best choice for choosing row or column is a row and column that have a lot of 0 in as its element, so it is easier to calculate it. So this is the formula, right? Let's not really be confused with the formula. It is just actually they are showing you how to calculate it. So how do you actually do the cofactor expansion? So first, we know that to look for cofactor, right, which is this C11, C12, C13, you should conduct a calculation on minor first. Okay, so for this calculation, they don't really show you the step of calculating minor, but it is embedded in there. As you can see, this is the calculation for minor 1 1, and then you have minor 1 2, minor 1 3. So basically, minor 1 1 means that we actually eliminate 1 1, that will give you this as the minor. And then for 1 2, so we have 1 2, so 3 2 4 1 as its minor, and then 1 3. So for 1 3 1 3, so this is actually its minor. So you just calculate the minor and then multiply it with 1 to the power -1 to the power of ij. Okay, that will give you the C for each element, the cofactor of each element. So what's new here is to combine multiply by the original element of each respected element in the selected row. So basically, if you are choosing the first row, meaning that you are choosing for A, you are choosing this one, so each of its original value need to be multiplied with the calculated cofactor just now. So we have 0 times with anything, you will get 0, and then A12 is 2, right? A12 is 2, this one, times with the calculation of cofactor for A12, right? And then you have A13. A13 is 1. So this is it, right? Times with the calculation of cofactor. So even though at first it looks a bit complicated, but it's really not, and it will still get you the last one answer for determinant, which is 14 for this case. But again, the beauty of using cofactor expansion is that you don't need to calculate for each of the element. You just need to choose for any rows or any columns. It can be this, it can be this, it can be this. But usually, to make things simpler, we are always going to choose a row or columns that contain a lot of zeros. For example, if you look at B, right, this is actually the best column to choose because it has a lot of zero. Will ease our calculation later on. Okay. Now, still, if the question asks you about determinant, then you can use it. You can use the cofactor expansion, right? Any column, any rows to find the determinant of that particular particular matrix. But if the question wants you to find adjoint, this is another, maybe the last subtopic for this video, find the adjoint. We are going to use adjoint later on in our calculation, but now let's just be familiar with it. So if they want you to look for adjoint, right, there is no other way around. You will need to calculate for the cofactor for each element, and then you are going to need to transpose it. We'll have done transpose before, where row become columns, columns become row. So transpose the cofactor, all of the matrix of the cofactors will give you adjoint, denoted as ADJ. So that is adjoint. So again, adjoint here is just a new matrix, right, formed from the cofactor. So in the next topic, we'll see how it becomes useful for building something called the inverse matrix. But for this chapter, your main goal is to practice how to find minus, cofactors, and the adjoint step by step. So I think that's it. So far we have learned how to form minus by removing rows and columns, and how to add signs later on to get the cofactors, and how to expand a determinant using cofactor expansion, and how to build the adjoint by transposing the cofactor matrix. So please keep this skill ready. They will be the tools for our next topics, which is inverse matrices. Thank you and Assalamualaikum.